Okay, so last time, I'll just briefly review what we did last time because there are a lot of formulas. So, okay, so we started with the Dirac equation written in this form with the Dirac Hamiltonian that is equal to C alpha P plus M0 C beta. Which day of the week it should have been? Friday. Okay, so we were looking for a general solution of this form. So this is an ansatz psi of x exponential minus IH ET. And if you plug these into this equation, you get E psi of x. You see this, there is no dependence on t. That means we have factored out a dependence on t here, equal HD psi of x. So now we have to find this form. This object is like the Dirac state, an object with 4 components, so psi 1, psi 2, psi 3, psi 4, and we call it phi chi, in the sense that this is an object with 2 components, this is an object with 2 components. You expected me for the tutorial? You knew that there was somebody else. I had already informed you. Okay. Now, if you insert this, so basically this is a parametrization. If you insert this into this and use as HD this expression, what you get is the following equation. So now into the eigenvalue equation we insert this, and what we get is E phi chi equals C. We remember the form of the alpha, so these are the Pauli matrices, times P phi chi plus M0 square C square 1, 0, 0 minus I phi chi. This if we use the form of alpha and beta that we are accustomed. Now let's make a further choice. That is the choice of having the state with definite momentum. So we further parameterize our state in this manner, exponential IH px. Okay, and note these are, now we have chosen a particular value for P. Let's put this form into this equation. You see this is an eigenvalue equation, that is this. And these objects are, each of them has 2 components. I have put in the alpha, I have put in the beta, and so on. So if you now insert this expression into this, so this is a choice we made, okay? Like this was another choice we made. We chose energy, we chose state at fixed energy, and now we chose state at fixed P. Then if you do this, these 2 equations becomes the following: E minus M0 C square I phi, this is the identity operator in 2 dimensions, phi 0 minus C sigma dot P chi 0 equals 0. And then the other is minus C sigma dot P phi 0 plus E plus M0 C square chi 0 equals 0. Okay, so basically I have brought, the term, this term on the other side, and so on and so forth, and put together the phi 0, chi 0. So this is an eigenvalue equation, and these are basically four linear equations, because each of them is two components, is equal to 0. So the determinant of the coefficient to have a solution different from 0, the determinant of the coefficient must be equal to 0, m0 c I, this is the c sigma dot p minus c sigma dot p e plus m0 c square I equals 0. So the determinant of the coefficient must be equal to 0 for this solution to be non-trivial. And now you have to use, as I said at that time, some property of the sigma matrix, because now this apparently is a 2 by 2 determinant, but actually it's a 4 by 4 determinant, because these are 2 by 2 matrices, these are 2 by 2 matrices, the sigma. So you have to use one property, one well-known property of the sigma matrices, that is the following. I'm just quickly reviewing what we did last time. This object is A times B, where A and B are two vectors that multiply the three sigma matrices, okay? Plus I sigma A wedge B, that is the vector product, okay? So this is a vector product, is a vector that you have to sandwich with sigma. Well, if you use that, then this determinant, all the calculation is a little bit long, but you get E square minus MC square I minus C square sigma dot P equals 0. Then for this one you use that identity. This P is 0 because P times P is 0. And what you get is that E square is equal to M square C square plus P square. So even from the Dirac equation, because of the property of the alpha, we knew already. Remember that one of the conditions we wanted is that the Dirac equation somehow gives the mass-energy relation, that is that one, and we actually, and if you remember, the form of the alpha and the beta was such to provide that, but at the operatorial level. Now, with this particular choice of solution, this one, and with this other choice that is an energy and a momentum eigenstate. So if I choose energy and momentum eigenstate of this solution, I get that the E must satisfy the well-known energy-momentum relation. Okay, this is very important, because now, well, of course, I have plus and minus M0 C square C plus P square. So, what do they miss?
M0 C raised to 4.
To the fourth.
Yeah.
But then there is a C here.
Okay.
C square. So there is MC4, and then there is a P square here, and there is a 4 here then. Okay. You know, now you understand why it's much better to put C equal 1, you don't do these mistakes. And so there are two energies. So if the Dirac equation solves the problem of the probability interpretation, it does not solve the problem of the two energy level. That means you always have positive and negative energy, and that is a problem. Now, the last things we did, I don't know if we did actually, is these two equations, the determinant is 0, they are equivalent. So we can derive phi 0 from chi 0 or similar things. So let's cancel here. Let's just remember that we chose a solution of the form phi chi exponential minus I h e t, and then phi 0 chi 0 exponential I h px exponential. So this, we chose a solution of definite momentum. Now the point is, well, does it exist a solution with definite energy and definite momentum? The answer is yes, it exists, but the momentum and the energy have to satisfy this. Okay, and now we have to build it explicitly. You understand? So what we have done is we plug in a solution with definite energy and definite momentum and ask ourselves, does it exist a solution to that equation? We turn that equation into an eigenvalue equation, and we prove, yes, it exists, and the phi 0 and chi 0 are different from 0 if the energy and the momentum satisfied. But which is the form? Well, the form you take from this. These two equations are linearly dependent, so you choose one from the other. You can choose one from the other. So, for example, let's choose this. So we know that chi 0 is equal to C sigma dot P over M0 C square plus EP phi 0. So given phi 0, we can derive chi 0. We knew that as it was an eigenvalue equation, they were not independent, and in fact, given phi 0, we can derive chi. Okay, so this is what we got last time. Maybe we went a little bit further, I don't remember. Okay, so we have an arbitrariness in choosing phi 0. We can choose phi 0 in the following manner. Phi 0, let's suppose, is a 2 by 2 vector that we indicate in this manner, or we indicate as u, and we suppose is normalized Okay, so we have total freedom in choosing phi 0, but chi 0 is then automatically determined. Okay, then if is automatically determined, well, let's first of all do one thing. Now we can label this state with the value of the energy, and we know it can have two, and the value of P. It can have two values of the energy. So the value of the energy, it was plus minus P square C square plus M0 square C to the fourth. This plus minus, let's call lambda, and let's indicate this with EP, in the sense that E, the energy, is an energy of that depends on P. So we put this lambda that labels the two value. Lambda is plus or minus 1. Okay, now we have chosen this phi 0 because it's arbitrary. Automatically we get chi 0. Okay, chi 0 turns out to be C sigma dot P over M0 C square plus, now here, you know, EP can have two values, so we can put lambda EP, and EP takes the modulus. So we get plus lambda EP U. This is the value of chi 0. But now that we have the value of chi 0, we can build the full solution. We have phi 0, that is this arbitrary two-vector normalized. We have got chi 0 from the eigenvalue equation. So we have both of them. Now we can write the full expression. The full expression is the following. There will be, I am just plugging in here actually. There will be a normalizing factor. Then I have the phi 0, but the phi 0 is u. And then I have the other, the chi, sigma dot P, M0 C square plus lambda EP in modulus multiplied by u. And then I have the exponential IPX minus lambda EP over h bar. And if I want, I can put the usual normalization so that this become gives the Dirac delta when we normalize it. Now, the only things to determine is the n, because it's true that the u are normalized, but there is this factor in front, so it might be that the psi are not normalized. So let's normalize them, and let's normalize in the following sense, that, you know, there is a wave there, so we have to normalize in the sense of the Dirac delta. So p lambda xt psi p prime lambda prime xt in d3x, we want that is something like delta p minus p prime delta lambda lambda prime. Okay. Yes. This column matrix is U, that is U is this object here. Then there is a U that is again a 2 by 2 that multiply these, that is a matrix 2 by 2. And C, sigma is the Pauli matrix, dot P, okay?
This object, is it a matrix?
Yes, the object is a matrix because there are the sigma. Okay, so this object is a 2 by 2 matrix that multiply column vector U that is 2 by, is a 2 column matrix column that is this. This is a 2 by 2 object, okay? Phi is a U1, U2, these things, these two. Then here I have a 2 by 2 matrix that multiply a U that is a U1, U2. So everything is correct. I have a 2 by 2 matrix that acts on a column made of two numbers. And so altogether, this is a 4 vectors like it should be. 2 here and 2 here, okay? So let's normalize. If you normalize in this sense and plug it in into this expression n, you get for n, I will not reproduce here all the detail of the calculation you can find on the book, and is the following. This normalization factor is m0 c square plus lambda EP over 2 lambda EP. Okay, I think we got here last time, but there were many formulas, so I don't know if I give all the details. So now we have everything. We have the normalization factor. So this is the things. What is still, we have the freedom, and this freedom nobody can take away, is the choice of U1, U2. We have only chosen that is normalized. Now note that the energy can be positive and negative, so there can be m0 c square minus m0 c square, and then all the states above, and then all the states below. Why? This is the minimum amount of energy in the positive case, and all the other energy are above. This is the minimum value that the energy can obtain, and all the value are above. The same for this. This is the minimum negative energy, and all the other are below. Okay? This is what happened. So now we have chosen a solution with fixed energy. So we have taken the free Dirac equation. This is the free Dirac equation. There is no potential. We have looked if there are solutions at fixed energy and fixed momentum. And there are solutions provided the energy and the momentum are related by the mass-shell relation. And we have found the explicit form of them. This is very important because it's the solution of the Dirac equation, you know. And we have found the normalizing factor and everything. So now, unfortunately, I cannot keep these here. Now, there is, beside the energy and the momentum, for the free Dirac equation, there is another quantity that is conserved, that is the helicity. Now we will define it. Unfortunately, this blackboard is small and I have often to cancel it and rewrite things, but Everything is on the book. I'm just taking from the book, okay? I'm not adding anything. Now let's define the following quantity, sigma, okay? And let's define the following operator. Sigma dot p, this is an operator, is this, sigma 0, 0, sigma dot p. So these are vectors. There are three, and there are the three sigma matrices. Now, it is easy to see that this quantity commutes with this quantity commutes with H. Now, we have to prove for this to commute with H is this. We have to P and P commute. We have to show that this commute with alpha and that then this commutes with beta. So let's see with alpha. Well, we have somehow sigma 0, 0, sigma. This is this part. Let's see if it commutes with alpha. And alpha was sigma, sigma, sigma. Okay, this was alpha. And if you do, so do this commutator, you get I, the identity I, okay. And vice versa. Now this is, so this is the sigma that enter into this capital sigma. We do the commutator and we get this. Let's do now the vice versa. 0, sigma, sigma, things, sigma, 0, 0, sigma. So this was alpha. If you do the commutator, you get exactly I, 0. So when you subtract one from the other, they commute. So we have proved that this commutes with alpha. Now let's prove that it commutes with beta. Well, sigma dot p and beta. So these basically, we have checked that sigma dot p with alpha commutes. Now we check that this commutes, and this as simple as, let's forget for a moment the things. We have sigma, 0, 0, sigma. Then we have to put the beta. The beta is 1, 0, 0, minus 1. Let's do the commutator, and here is easy to see. Of course, the commutator, you have to remember that now is 2 by 2. This is 0. Okay, so this quantity that is called the helicity, you see, if the sigma of Pauli are related to the spin, this is the projection of the spin onto the momentum. Okay, so imagine the momentum of the particle is this, and the spin is pointing in some direction. I don't know. This is this object is the projection of the spin on the P. Okay. So the three quantities that we can diagonalize together is the Hamiltonian, P, okay, because P, we see that it commutes with the Hamiltonian, because P and P commutes, here there is the identity. P is an operator not in the spin space, in the 2 or the 4-dimensional space, but in the Hilbert space, so P and P commutes, and now you have seen that sigma dot P commutes. So we can diagonalize these three operators. Now is another quantity that is related to this sigma is one that is divided by C, and is this actually the helicity operator. The helicity operation is the following one. It has an H over 2 sigma dot P divided by the modulus of P, and this is the usual spin operator that is H bar times the sigma matrices P over modulus of P. Okay, and this, okay. So from here you see that is the projection along the direction of P normalized by P. And so as all these three commutes, or lambda S commutes, you can label the eigenvalues with these three numbers. Okay. Now, let's now go and choose a very particular solution. Let's choose one in which P is moving along the Z direction. Can I cancel here? You know, this is the free Dirac equation. If I had put some complicated interaction, it might have been that the helicity don't commute anymore, or that the momentum don't commute anymore. You know, if I put here a function of x, then P doesn't commute anymore, because P and x don't commute. So now let's make this choice. Let's choose P to be only along the Z direction. And then let's build this object. We know the sigma, but P is only along the Z direction. So sigma is also, the only sigma that enters is the one along the Z direction. And what we get is that the helicity operator is basically h over 2, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, minus 1, 0, 0. Okay, so this is the helicity in the case that the momentum is just along this direction. You see that these, which matrix did we use here? The sigma z, because there I have the scalar product between S and P, but P is only along Z, so I only need the sigma Z. And now let's diagonalize these. If you diagonalize these, you get 4 eigenstates that are these. Let me, for the moment, write in this manner. Where U1, so this is 2 by 2 and this is 2 by 2. This 0, it means is a row of 2 elements, 0 and 0. This is a row of 2 elements different from 0. Which are the elements? U1 is defined U1, 0, and U minus 1 is 0, 1. And the eigenvalue, so we are diagonalizing this, the helicity operator. By the way, I never wrote down, so helicity with the H. And here, instead of this, I can use lambda S. And capital sigma, it means you have a 4 by 4 matrix whose entry on the diagonal things are just the Pauli matrices. Okay, so this is the helicity operator. It has 4 eigenstates. Of this form, where U1 and U2 and U minus 1 are these. And the eigenvalue of these are plus and minus H bar. Okay. Or H over 2, I think. Now, for this kind of solution, let's write down the full wave function as we wrote before. So we can label the wave function with E, P, and helicity. And let's now choose solution that move along the Z direction. Then the solution are just the following one. We have psi, P, then the two value of the energy. So we put lambda. Then we have this helicity that can be plus 1/2 or minus 1/2. Psi, P, lambda, minus 1/2. You know, there are 4 because this can be plus minus 1, this plus minus 1. Now, the solution, remember the form, we have this object, we had the n. The solution just come out to be the following: G sigma Z P m0 c square plus lambda EP. N is that normalizing factor that we found before, exponential IPZ minus lambda EP times T, all these over H bar, and this one is N. Now the other solution you see here is with 0, 1. So this is the helicity eigenvalue. I put H bar equal to 1. Okay. The other solution is 1, 0, C sigma Z times P m0 C square plus lambda EP 0, 1 exponential IH PZ minus lambda EP times T. Okay, so these are the 4 solutions of the free Dirac equation with momentum moving only along the Z direction, okay, with energy EP that can have 2 signs, and with the 2 possible values of the helicity. So these are the 4 solutions, and they make a complete set, okay. Well, N we have found before, but let me write it. N is square root of m0 c square plus lambda EP divided by 2 lambda EP. Okay, these are 4 solutions, and they make a complete set for the Dirac equation. A complete set in the sense that psi dagger P lambda S Z psi P prime lambda prime S prime Z d3x equal delta lambda lambda prime delta SZ SZ prime delta PZ minus PZ prime. So they are complete. They are a complete set in this sense. They are orthonormal and complete. And this is the orthonormality relation. Now, okay, so it's possible to work out the complete solution of the free Dirac equation. It has this form. You can say, oh, but you are along Z. Well, choose any P, any along direction, and then rotate the axis so that that axis is Z, and then this is the general solution. So this is the general solution where Z, the Z we choose here, is along the direction in which P is. Okay, and the eigenstates are labeled by the 3 eigenvalue, P, lambda, that means the energy, and the helicity. Now, there is an important concept that we will introduce. So this is mathematics. Now there is an important conceptual object that we have to introduce. We have seen that there is probability interpretation. That means with the Dirac equation, we have the probability interpretation that was not present with the second order equation. So that means the rho is psi dagger psi for the Dirac equation. So it's positive definite. Each of them is nothing else than psi1 star psi1 plus psi2 star psi2 plus psi3 star psi3 plus psi4 psi4. So as I repeated and repeated many times, starting with the first order equation, we have and forcing the alpha and beta to have those particular anti-commutation relation, we have been able, the price we pay is a multi-component vector. It's not one, like in the case of the Klein-Gordon. So we have to introduce matrices, and the price we pay is that then these are also vector in the internal space. But there is positive definite of this. The only thing is that the energy, even if it's satisfied because of the commutation relation between alpha and beta, the mass energy relation, it can be plus and minus 1. So plus minus 1 and the expression there. So it can be positive or it can be negative, and the minimum is m0 c square, and here m0 c square. So one can say, well, for the negative one, we give an interpretation like antiparticle and so on, but we have seen that there were problems with the Klein-Gordon, that we cannot give a single particle interpretation. As soon as we probe a distance that is less than the Compton length, there are many particles being produced, and so and this is due to the negative energy problem. But there is a further problem that we have not addressed in the Klein-Gordon. If you have a particle here, usually the particle tend to, if we subtract energy to this one, it can go down, down, it can even jump down here, and it can go bottomless. So it can go, and usually a particle loses energy to radiation and so on, and it comes down, and then this particle can go, is bottomless, this potential. So that is a problem that was not solved in the Klein-Gordon case. Actually, I did not even mention, but it's a problem. That means an energy, a system can have minus infinity as energy. If you keep continuing taking energy off a particle, she can continue going down. Now, can we solve, so this problem was solved. Yes?
In this process, where the particle can pass from upper level to the lower one, can we say that the particle become antiparticle? Because we know that
Yeah, but you see,
have this one which have this negative.
right, right. It can, you will see when you do field theory that it can become an antiparticle. There is a process, but you don't have the tools, and it would take 3 months to give you the tool that a particle can turn into its antiparticle. It's not a problem. The graph is this. Okay, you can interpret a particle as being an antiparticle, but is the same particle going forward, going backward in time. But let me not enter into that detail. So a particle can be turned into an antiparticle. The only problem is the following. So it can go down in energy to any level, and it can reach, usually we want something that has a bottom, that is our ground state. Okay, we don't want something that has no bottom like here. Now Dirac solved that problem for the spin, for his equation. So the bottomless of the potential so no ground state. Dirac solved it, and he solved in a funny manner. So let's suppose this is our, so this is minus m0 c square, m0 c square. We will see in the next things that we will do that the Dirac particle carries spin 1/2. We will do the non-relativistic limit. We will see that it carries spin 1/2. So he had this idea. For a particle not to double down and go there, he said, let's suppose that these lower energy things are full with electron. Each level has 2 electrons. One will spin up and one will spin down. Then a particle can come down here, come down here, come down here, come down here, and come down here. But it cannot go here because this is already full. You cannot put another particle. There is already, for the Pauli principle, you cannot put another particle here. So this is called Dirac C. The Dirac C is all the negative energy state are filled with plus minus 1/2 spin particle. In that manner, you can see, but where do you see them? Well, he called these, well, it's an hypothesis, a theoretical hypothesis, but if it were like that, then we would solve the problem that there is a bottom. So the ground state in the Dirac case is the Dirac sea, is all the negative energy levels are full of particles, okay? So he solved the first problem, he solved the second, but you see again, it's not a single body equation, because to solve it, he had to populate this level with particles, and so he had a many particle system. So to solve one of the problems that is the bottomless, the fact that the potential is bottomless, he had to introduce an infinite number of particles. So also his formalism is not anymore a single particle form, but at least he managed to solve a couple of problems. Yes?
How does he populate the electrons in the sea?
No, it's an hypothesis. It's just that he said, if it were that at each level, and you can say, how can you see the things there? Actually, what you see is that if you pull this out, there is a hole left there, and that hole can be interpreted as antiparticle. Okay, but I will not enter into this. That means if you hear, I only wanted you to know the concept of Dirac sea. The Dirac sea means all that is an hypothesis by which that says that all the negative energy are populated each level by 2 spin 1/2 particle, and so a particle in the negative energy things cannot go down there. Yes?
It seems like there is a barrier potential between the two levels. Because if the electron cannot, the particle cannot move from
Yeah, it's something like if there were a potential, an infinite barrier potential. But you know, the Pauli principle is exactly that. If you have 2 particles on a shell, if you have an atom, and one energy level is already populated with 2 particles, spin 1/2, 2 electrons, one spin up, one spin down, no other particle can come there. So it's something like if there were an infinite potential. The Pauli principle itself is like that. Now, yes?
what if the energy of the particle is big than this potential?
What?
If we have a particle with big, okay, enough energy.
No, it cannot, because it would violate the Pauli principle. So, you know, it's like, do you have enough energy to violate the Pauli principle? No.
Ferromagnetic say we through the
You can violate the Pauli principle, period.
no.
So you can have all the energy you want, but you cannot violate the Pauli principle. So that means you can have a particle with infinite energy here that try to go there, and it cannot go because there is the Pauli principle that says you cannot come.
So
You know, you are visualizing things. That is the things you should not do in quantum mechanics, and especially in relativistic quantum mechanics, because you are a big body, okay, so not a microscopic object, and so you don't know, you cannot really somatize the quantum law of motion, and at the same time, you are not going at the speed of light. So don't try to visualize things. You are trying to visualize things, and I'm telling you, don't do it. You are heading against a wall, okay? If you try to visualize things, and you know, there are many visualizations you can do here, they are all wrong. Just, you know, I like to look at quantum mechanics. It's something that we don't visualize because we are big object. We are not the size of an atom, so we have different law of motion, you know. And what I say is that as you cannot visualize, you have to take quantum mechanics as a part of mathematics with a set of postulates. You know the postulate of quantum mechanics and the consequence you derive. Now, can you visualize in mathematics? There are things in mathematicians write down, oh, let's work in a space with infinite dimension. Can you visualize a space with infinite dimension? Or can you visualize a space with 5 dimensions? Huh? Yeah, but you cannot visualize. That is physics. And you, as a body, you can only visualize the things that you can experience. And you have ever touched an electron? Huh? Have you ever touched an electron and say, I take it and go? No, you can do it, but you will touch many. Put your finger inside the electric thing, socket, and then, but you will feel the effect of a trillion of electrons that come through your blood and your skin and so on, but not one. So that is trillions of electrons, a macroscopic thing. So here is the same. If you imagine where you wanted to go, but if you have enough energy to go down there, no, you don't. You cannot have enough energy because there is the Pauli principle. The Pauli principle is a postulate, and it derives from something else. I mean, I'm sorry that I abruptly stop you, but it's also, you know, is the manner, I want to tell you the manner you should approach quantum mechanics. I teach quantum mechanics at the university, and I always tell my students, don't try to visualize anything because it's impossible. I mean, what I would like is I would like to be transformed for a week into an electron. And then I see and I come back and I say, oh, now I understand everything. It's not that you understand. Doubt that you can visualize better what the law of quantum mechanics tells you. You know, it's been a big effort to be able to derive the law of quantum mechanics without being an electron or a microscopic particle. Then you have to, as they work, you have to accept them, and I accept them like a piece of mathematics. For me, quantum mechanics is a piece of mathematics with some postulates that have no contradiction among themselves, from which you derive theorem and so on and so forth. So, yes?
Okay, here we have a graph of energy 2m0 c square, right?
Mm-hmm.
Does it mean we have zero energy? I mean, we have minus. And then
Yeah, but on that things there is no state, because if you have a particle with mass, its minimum energy is m0 squared. Okay, now let's do as we did. That means let's look at this psi, not as a wave function, but as a field. And let's see if there is a Lagrangian from which we can derive the equation of motion. So let's now look at psi as a field and not as a wave function. And let's see if there is a Lagrangian from which we can derive the things. Well, let's use notation that is more common and we will use, that is the one of the gamma matrices. Let's define 4 gamma matrices defined in this manner. Gamma 0 is beta, and gamma I is beta times alpha I. These are so-called gamma matrices. And then let's define for psi something that resembles the dagger, but is psi dagger multiplied by gamma 0. Okay, this is the definition of psi bar. It's called psi bar. This is psi dagger multiplied by gamma 0. This is a very important object. Now, as a psi, as a wave function, also as a field is a complex object, we can have psi that has 4 components and psi star, but you know, psi star is the same as this one, so from now on, the degree of freedom that we will consider is psi and psi dagger. And altogether they are 8, because each of them has 4 components. These has 4 components that are different because they are the complex conjugate multiplied by gamma 0. So if they ask you how many fields do you have in the Dirac equation, 8. Okay? 8 fields. Even if I indicate them in these things with just 2, they are 8. Because this object is psi 1, psi 2, psi 3, psi 4. Because, you know, it is applied on a 4x4 matrix, so it must be a column. And this one is psi 1 star, psi 2 star, psi 3 star, psi 4 star, multiplied by gamma 0. It is a 4x4 matrix, and is like beta. Okay, so altogether we have 8 independent objects. Now, the question is, can we write a Lagrangian that depend on psi dagger, psi, the mu psi dagger, such that this equation of motion are the Dirac equation of motion? That is the question. The answer is yes, it's easy. The Lagrangian is the following: psi bar ICH gamma mu d mu minus m0 c square psi. So there is a Lagrangian that is this, that reproduce as equation of motion the Dirac equation of motion. So I can look at psi both as a field and as a wave function. Okay. Now this one, let's now write a psi as a psi dagger gamma 0 and so on and so forth. So if you do psi dagger gamma 0 ECH, then gamma 0 dCt plus ICH gamma I dDi plus and so on and so forth. Go on. Then if you do this, you get the following equation: psi dagger EH ddt minus C alpha times P, and alpha is an operator, minus beta m0c psi. Okay, so another form of the equation of the Lagrangian is this, but you see how awful it is. It has not the right things in the right place. I mean, you have to remember by heart. This one is much more simple. Thanks to the gamma function and the use of the psi dagger, this form is very compact. Okay, you see. So gamma mu, the mu. So now let's see if this is true. That can we derive the Dirac equation from that Lagrangian? I will only show you one thing. Let's remember we have to derive the equation, we have to build the action. The action is L d for x, because that is the Lagrangian density. And then what we have to do is we have to do the variation of S with respect to some of the field. Okay, so let's do the variation with respect to psi bar. If we do the variation with respect to psi bar equals 0, this implies this is the variation of the action equals 0. These are the equation of motion, and are the analog of the Lagrangian equation of motion that you have derived from a variational principle. This one is dl d psi minus the mu dl d the mu psi bar equals 0. That this object implies this, we have seen already when we did the Klein-Gordon equation, okay? That this variation of the action implies this, and this, you know, is the analog of dl dq minus dt dl dq dot equals 0. This is the analog of that. It's just that instead of time now we have 4 space-time, and instead of q we have the field. Now let's do the variation with respect to psi bar. You can ask, why do you do with respect to psi bar? Well, if you do with respect to psi bar, and let's choose this. So let's cancel this part. Let's choose that. And let's do the variation. If you do this, you get the following thing: CIH gamma mu the mu psi minus m0 c square psi equals 0. So I have done the variation of that Lagrangian with respect to d psi. If I do with respect to d psi, you see I get from d psi bar, I do the variation with respect to psi bar, so I get all the rest applied on psi equals 0, right? And that is this. And this now, let's go to the alpha and beta variable. If you go into the alpha and beta variable, you get IH ddt psi equal alpha p plus beta m0 c square psi, and this is the usual Dirac equation. So we can get the Dirac equation, but it's funny. To get the equation of motion for psi, we have to do the variation with respect to psi bar, and vice versa. I will not do the vice versa. Is written on the book, and you will see, you can look at it on the book. So there is a Lagrangian in which we can look at the wave function of the Dirac equation as a field, and that Lagrangian is very simple. It's also very simple to remember. Just take the Dirac equation, that is this equals 0, and multiply by psi star. And then the equation of motion, you get it. Now, as there is a Lagrangian, one can immediately say, is there also an energy momentum tensor? Yes, there is an energy momentum tensor. Is the usual definition. The energy momentum tensor is you take the degree of freedom you have, you do the derivative with respect to that, multiply by psi. Then we have another degree of freedom that is psi bar, and so we do, and then we subtract the Lagrangian. That is the usual definition as we did with the Klein-Gordon. With the Klein-Gordon there was only this piece, where this was a psi, this was the derivative. Now we have another piece. Why? Because the degree of freedom are 8, but we have collected them together into psi and psi bar, so in 2. Well, if you work out these, do the derivative and do this and so on, I don't want to work it out here, but what you get is the following expression: psi bar IHC gamma mu, the nu psi minus delta mu nu psi bar IHC gamma sigma d sigma psi plus delta mu nu m0 c square psi bar psi. Okay, so this is the energy momentum tensor. Which is the use of it? The use of it is that one component, if you remember, the T00 is related to the energy density. So let's see if that is the case also here, if this is related to the energy of the system, that we know the energy of the system, because we had derived for the free Dirac case. So let's take the T00, take that expression and put the T00, and what you get is psi daga alpha times P C plus beta m0 c square. These are operator psi. But this, what is this? This is nothing else than the Dirac Hamiltonian. So we get psi daga HD psi. So if now you do the integration over d3x of this energy density, you should get the energy, right? But in this case, it means d3x psi daga HD psi. And this is nothing else than psi HD psi. So is really the expectation value of the Hamiltonian. So we have proved that interpreting psi as a field, we can build a Lagrangian, we can build an energy momentum tensor. Out of that, we can get the energy density, that is the T00 component. And then if we integrate the energy density, we should get the total energy. Is it true? Yes. We get an object that is exactly the expectation value of the Hamiltonian, so everything fits. Another quantity that is interesting is the trace. You will see next year if you do field theory. You already know where you will go next year? Each of you? Okay. Now, let's take the trace. The trace of the energy momentum tensor is very important because it enters what is called the trace anomaly, and most of you will do next year when you do field theory. Let's take the trace. T mu mu means we sum over mu. So we start from here and do, and use the equation of motion because we suppose that the psi satisfy the equation of motion. You get m0 c square psi daga psi. And you know, immediately you imagine that this is proportional to rho, the energy density, the probability density, but it's not so. This is psi daga. while rho, it was psi thing. So the trace was psi dagger gamma 0 psi, because this is psi dagger gamma 0. Okay, so note the difference. This is positive definite. The trace might not be positive definite. This is positive definite because it's just the scalar product of psi with psi. This might not be positive definite because it's not the scalar product of psi with psi, but often there are, of course, you can write these also. If you say, I don't like to use a psi dagger, can I use psi bar? Yes, you can do psi bar gamma 0 psi, because this is psi dagger gamma 0 psi. Gamma 0 was beta, you know that the square is 1, so you get psi dagger psi. So you want to write the probability density using gamma 0, then you get this expression, okay? Sorry, I'm going a little bit fast, but these are formal things. What I did it slowly last time and repeated this morning, it was the solution of the free Dirac equation. Okay, that one is a very important piece of information. So on that one, really spend some time in the book where it's worked out. Now, to find out, you know, there are all these problems with the Dirac equation, with the Klein-Gordon, with the relativistic equation. They cannot have a single particle interpretation. There is this issue of negative energy. To solve for the spin 1/2, you have to do this business of Dirac, of the Dirac sea, and you might like or not like our friend there and so on, but, and I also personally don't like. In fact, all these will be solved when you quantize this field. Looking at this as a field is a generalization to infinite degree of freedom of the point Q, the position Q, and you know that when you do quantum mechanics, you quantize. Q become an operator. You will see when you do quantum field theory that you will make this into an operator. So this that was a wave function, but actually can be interpreted as a field, will be quantized. Quantized in the sense it will become an operator, and then all the problem will be solved, at least part of it. There is a problem that is called renormalization that you will attack next year on that. But now let me show to you another of the funny things of the Dirac equation. And is related to the concept of velocity. Let's suppose, and it tells you that you cannot have really an interpretation as single particle. Let's take the Dirac Hamiltonian. The Dirac Hamiltonian is written there. Is C alpha times P plus beta M0 C square I put a C here, and then I have a C square here, or otherwise I have to put things everywhere. Right. Okay. And these are operators. Now let's stick to a single particle interpretation, and let's think that the velocity is the derivative of dx dt. And then let's suppose that we do the commutator between x and hd. But you know, if you do the commutator of this with this, what do you get? X feels something that doesn't commute on here in p, with the other it commutes. So here you get as velocity c alpha. So the velocity is proportional to the matrix alpha. But the matrix alpha has eigenvalue plus and minus 1. It means the velocity of a particle, of a Dirac particle, is plus or minus the velocity of light. That means it moves along the light cone, you know. If you have the light cone, the particle can have either plus c or minus c, because the eigenvalue of alpha are plus minus 1, the eigenvalue. then is multiplied by c. So a Dirac particle can have only c and minus c. This is crazy because it has a mass. It cannot go the velocity at the c. So it means something is wrong here. And what is wrong is to interpret x and p as conjugate variable, and that you can do, but you do when you have a single particle interpretation, okay? Actually, if you do relativistic mechanics, you know that the velocity is c p over ep. This is the velocity of the particle, and this is not c. Actually, the velocity, this velocity is something like this. So these strange things is if the particle, this is the true velocity. If the particle keep moving across these other things, doing a sort of zigzag, and this effect, this strange effect that actually does not happen, but is called, they use a German word because the physicists that discovered it were German, and it's called Zitterbewegung. And in German, I don't know German, but in German it means trembling motion. And it is the trembling motion of this particle that apparently moves at c, but keep changing c from c to minus c. And so this trembling motion around the true trajectory of an electron is called Zitterbewegung. Just to tell you one of the many funny things about yes, what we will skip is well, we will skip, but please do read it, is the energy of the solution of the free Dirac equation derived from T00. If you take from T00 and integrate over D3x, we have found that is HD psi. But we have not found that is E, the E that we used before. So what we will not do is insert here the solution that we did at the beginning of the class, do all the calculation and see that this, put in all the normalizing factor and you will get E. So that means it has really the meaning of energy. If you don't believe in this as an Hamiltonian, then do this calculation at least explicitly and see what happened. You will get E. We will skip that. It's a long calculation of no use to understand the physics of it. What we will do now, I keep telling that the Dirac equation is a spin 1/2 particle. Where does that idea come from? That is a spin 1/2 particle. It's true, there are the alpha matrices that contain sigma, and so the sigma of Pauli were the sigma of Pauli were somehow related to spin, but how can we really get convinced that these particles are spin 1/2? What we will do is this. We will do the non-relativistic limits. That means we will suppose that the particle velocity is much less than the velocity of light. And we will see that the equation that we will end up is the equation of motion of the spin 1/2 particle. You know, the velocity does not affect the spin. So if at low velocity it was spin 1/2, it is spin 1/2 also at high velocity. Okay, so what we will do is the non-relativistic limit of the Dirac equation. Well, we will only start today because it's a very long calculation, and to the person who should have done the tutorials, I gave the problem I already gave to you as homework, not the second set, but the first set, so that he does not waste time repeating problems similar to those. Okay, I hope he has understood. And okay, so we do the non-relativistic limit. that means V much less than C. That means we will neglect all effect of order Vc square, we neglect. Okay. Well, first of all, in order to do that, let's to do this non-relativistic limit, let's couple our particle with an electromagnetic field using, so P, let's suppose turn on an electromagnetic field. Okay. Well, if we do that, we all know that there is the minimal coupling rule. And let's see what the equation becomes. So P0, that is HT, P0 is the derivative with respect to x0. x0 is CT, so is here. You multiply by C above and below, and you get the derivative. You have to subtract A0. So this equation via P that goes into a mu goes into the following equation: CIH ddct minus E, sorry, here I put an E over C. E is the charge, because if I put on an electromagnetic field, it will have an effect if the particle has a charge. So this is the charge of the particle, this is the velocity of light. So EC over A0 psi equal C alpha minus ECA plus beta M0 C square psi. So I have done the minimal coupling here and here. I have put here a CT because in that manner this is x0, and then with x0, because of these things, we know that I have to add E0, but then I can cancel the C. So now if you simplify things, you get IH d psi dt equal C alpha times P minus E over C A plus EA0. I have brought the A0 on the other side, and the C cancel. So I have just EA0 plus beta M0 C square psi. Now, to study the non-relativistic limit, that is our goal, it's better to use a two-component formalism. So let's use the two-component formalism. Let's indicate in this manner. And each of them, phi tilde is a psi1, psi2, and chi tilde is a psi3, psi4. Okay, so let's use this formalism. Look, this is not, I put a tilde because this is not, this psi and chi are not the one of the first order formalism of the Klein-Gordon, okay? They are different objects. Let's us remember also the form of alpha and beta. Alpha is 0, 0, sigma, sigma. These are the three sigma matrices. And beta is identity, 0, 0 minus the identity. Okay. And the other things is, let me call, in order not to carry on always, let me call this pi mu, the Greek pi. Then this equation, now plug it in this here, plug it in this here, okay? And let's use the form of the alpha, let's use the form of the beta. Let's remember these things, and we get the following equation. IH d dt phi tilde chi tilde equal. Now let's put in explicitly the form of the C. If we put in explicitly the form of the C, we get C sigma dot pi chi tilde C sigma dot pi chi phi tilde, this is a 2 by 2 things, plus C A0 phi tilde chi tilde plus M0 C square phi tilde minus chi tilde. Okay? So I have put in these 2 by 2 components here. I have used the alpha that are 4 by 4 matrix but written with 2 by 2 blocks. And then instead of carrying every time the things, this one, for example, is pi tilde, I've called in that manner. And then you get this equation. Now, let's further simplify this. So this is an equation. You see, there are two equations for the two components, but they are coupled. You see, if you take the upper two, you have the equation of motion of phi tilde relates to a piece that contains chi tilde. So these are 2 by 2 equation. Altogether is a 4 row. Is a row with 4 things, but it's 2 by 2, and they are coupled because here it enters chi, here it enters phi, here chi is coupled with phi. The motion of chi is related to phi, so they are coupled with partial differential equation. The system of coupled partial differential equation. Okay, now let's do a further things. Let's simplify things in this manner. Let's write phi chi. Let's factor out the mass factor I m0 c square over h times t. I can always do. This is the definition of this object. That means I write that phi chi in this manner. You can say, can you do? Yes, of course I can do, because this is the definition of this object. So this object was the old one multiplied by a phase that is the opposite of this phase. So let's do that. Let's factor out that. And now let's insert this solution into here. Okay. Then I will have an equation for phi and chi. Okay, so I have just factored out the mass part. This I can always do because it means phi and chi are this one multiplied by the opposite phase. Let's see then which equation we get. Let me write that equation. Okay, so I'm inserting there, and I get this equation. IH d dt phi chi equal C sigma dot pi C sigma dot pi chi phi plus E A0 phi chi minus 2 m0 c square 0 chi. You see there is an object that has become 0. Okay, now this is the final equation we have got. I am taking literally everything from the book, okay, so means even if you have not written down everything. Now, this is the equation. It's still a 4 by 4 equation. So it does not look as a spin equation. At most, a spin equation has 2 components. But now let's remember one thing. For example, IH d chi dt is the total energy, right? The usual derivative with respect to a function is proportional to the energy. And this object, if we are non-relativistic, will be much less than m0 c square chi. That means the total energy of these, okay, will be much less than the mass. We are in the non-relativistic limit. So basically, we can say that if we are in the non-relativistic limit, it means the energy that comes with the mass is very big with respect to all the rest. Okay, so if this is, we consider this as the potential and kinetic energy, if we are in the non-relativistic limit, it will be much less than the energy coming with the mass. So this is called the small component. And the same, the E0 chi, that is the potential energy, will be much less than the energy coming with the mass. Okay? You see, in fact, if you look at the equation, look, here there is this part, here it contains P, is the kinetic energy. Then there is the potential energy, and then there is the mass energy. So we can consider that this actually is all the energy, and you cannot say all the energy is less than the mass energy, because the mass energy is less, is part of the energy. But let me consider that this is a good approximation. That means when you take the derivative and neglect, why I can neglect the mass energy? Because I remember that in the solution I factor out. You remember that in the solution, in the psi tilde was phi exponential minus I m0 c square t. I have factored out the mass energy. So if I do the time derivative of these, I don't get the mass, I get all the rest of the energy. And the same for the other. Chi tilde is equal chi exponential. This is in the book, is not explained very well. He just said small component and I component, but this is not the chi tilde, it's the chi where the energy is already factored out. So this chi carries only the kinetic energy, not the mass energy. Then you can say that is much less than the mass energy if you are in the non-relativistic limit. So, okay, this holds in the non-relativistic limit. Okay. Now let's stop here. We will start tomorrow again at 11. This week and next week is 3 classes per week we have. The last week instead we will have only 2. We will start from here, and as there is a lot of material to cover, I will, many of these pieces that I have done in the book are part of the theory and part of the exercise. You see in the book there are exercises, so I have not distinguished, but I have worked out exercises. So if somebody comes for the tutorial, say the exercises that Godfrey has done beside assigning homework are those that are in the text of the book called exercise, okay? So for example, what we did before with the energy momentum tensor was an exercise, okay? Okay, so tomorrow we will continue from here.